Uh, Hi everyone, it's VSA Online here, and I'm happy to introduce our two speakers for today. So today we have two shorter talks, but from the known group, so VSA Online and VSA Community from IBM Zurich and ETH Zurich. So please welcome Michael Hersche and Giacomo Camposampiero. So if I pronounce your surname correctly, they will introduce their topics in due time. So without any further delay, I leave the floor to you guys. So please.
All right. Thanks a lot, Evgeny, for the nice introduction and also for giving us the opportunity to present our works. So I will start with a work of the title Factorizers for Distributed Sparse Block Codes. And this work was a collaboration between IBM Research and ETH Zurich and has been recently published at Neurosymbolic Artificial Intelligence Journal. So in last year's VSAONLINE talk, let me quickly, I have an issue with the, so now. So yeah, in last year's VSAONLINE talk, I presented the paper, A Neurovector Symbolic Architecture for Solving Raven's Progressive Matrices. This was published at Nature Machine Intelligence. And the goal there was to tackle the problem of solving Raven's progressive matrices. We have a 3x3 grid, and the task is to find out the content of the empty panel at the bottom right by first finding out the rules and then executing them in the last row. And we approach this problem with a two-step architecture in a neurosymbolic fashion, where we first have the NeuroVSA front end, the perception that is able to map individual panels to a high-dimensional distributed representation using a trainable neural network, and then kind of infer the objects in this high-dimensional space using VSA codebooks and their operators. And then in a second step, we could use this knowledge of the objects by performing reasoning, meaning the rule detection and execution using distributed VSA representations and their operations. So we present tonight essentially two enhancements, both on the NeuroVSA front end and the back end. In the NeuroVSA front end, I will present a work, as I said, from the Neurosymbolic AI journal that solves combinatorial search with block codes factorizers. And then in the second part, which will be presented by Giacomo, we will have a work that has been presented at the NESI conference this year, where we replace the hard-coded rules by learnable rule formulations. So let me start with the NeuroVSA front end and have a short recap how we performed representation learning over these nested compositional structures. So let's say our task is to recognize objects, geometric objects in a scene. Then what we do in our NeuroVSA front end, we first initialize codebooks for all the possible attributes that these objects could take. For example, we have different types, different sizes, colors, or location. In each of those codebooks, we store code words, whereby the code words are just randomly drawn dense bipolar vectors. And for representing a combination of these attributes, we simply take the corresponding code words and bind them together with the Hadamard product. So we can do this for all of the possible combinations, which gives us then this so-called W matrix. Now, for recognizing or inferring which object is present in this panel, we can use a convolutional neural network, for example, ResNet 18, that is trained to map this visual input to a distributed vector representation. And this query can then be compared to all the possible bound representations. And we will get somewhat a similarity vector from which we can then take the maximum element. This solves some of the fundamental problems of neurosymbolic architectures, like the binding problem or the superposition catastrophe. However, we face a combinatorial search where we have to search over 6,600 different possibilities. So one way to approach this combinatorial search is to use factorizer networks or resonator networks. So these networks have been proposed initially by Freddie and Kent and colleagues in neural computation in 2020. We then enhanced these networks by introducing an in-memory factorizer that is able to achieve much higher operational capacity by using the inherent stochasticity of the in-memory computations and new nonlinearities. More recently, we also have seen a work by Renner and colleagues that further extended and port these resonator networks to spiking neural network hardware. So the general architecture approach of resonator networks or factorizers is that we want to iteratively update our estimates for, let's say, a type, a size, color, and location in this example. And such an update looks as follows. So first, we take our query vector and we unbind the current estimates of the other factors, meaning size, color, and location. Then we take this unbound estimate and compare it to all the possible elements in our code book. And this gives us a attention value, which we can feed through a nonlinearity, or we can also add some stochastic noise to it. And then this kind of manipulated attention vector, for example, sparsified attention vector, is then reconstructed. And we then apply the sign function to get, again, a bipolar vector. So in this case, I'm always talking about the bipolar dense factorizer. So we have seen in multiple works that it is actually possible to factorize such representation where we get mappings of synthetic images like these objects in Raven's progressive matrices. In this work, we wanted to go one step further and go towards natural images. For example, in the ImageNet 1K dataset. So here, when looking at the standard convolutional neural network, we see that after the convolutional layers, we have normally a fully connected layer that stores as many embedding vectors as classes. And these fully connected layers can become quite dominant when counting the number of parameters. So especially when looking at somewhat compact networks like the ShuffleNet V2, we see that 44.5% of the parameters are actually in the large fully connected layer, meaning there is quite some capacity or need to densify or compress these layers. So that's actually what we did. So we replaced this fully connected layer by a fixed bipolar fully connected layer. This fixed bipolar fully connected layer has a certain structure whereby we simply represent each of the class embeddings as a binding of two distinct factors. So we have, in this case, two code books, and for each of the code books, we have m number of entries or code words. With this, we can fix this bipolar fully connected layer and simply retrain or train the convolutional layers from scratch. Afterwards, for a efficient inference, we can apply a bipolar dense factorizer. However, what we have seen is that this integration is actually not straightforward. So when looking at the accuracy on ImageNet 1K, we achieve with the baseline with the MobileNet V2 71.3% accuracy. With the bipolar approach, when having the brute force search, we can maintain a high accuracy, like within 1%. However, when using the bipolar factorizer, we see quite some significant drop, which is more than 10%. even though we invested quite a lot into the different loss functions. So at the beginning, we were like at 50 and we could increase it to 60 by using dedicated loss functions. But this is somewhat where it ended for us. And we had to look for a different approach. And we were mainly driven by kind of some sparse natures of some of the convolutional neural networks that motivated us to look into sparse representation instead of the dense bipolar one. And one of these sparse representation is the binary sparse block codes, or short binary SBCs, which divide the d-dimensional vector into b blocks. And in each of the blocks, we just have one non-zero element, whereby all the elements in the block are set to 0. We have then also like segment length L, which is the dimension d and divided by the number of blocks. We also have a set of well-defined operations. So binding is the modulo L sum of the non-zero indices. Likewise, the unbinding is the modulo L difference. Then the bundling is simply the argmax of the sum, and the similarity is the dot product. This representation seemed quite amenable for neural networks, but it was not sufficient to use it for factorizers. So we had to relax the sparsity constraint, especially because we had this weighted bundling at the reconstruction side. So we came up with an additional representation, which we call generalized sparse block codes, where we relax the constraint of having a binary blocks, but the elements in the block can have any value. The only constraint that we put is that the sum of all the elements has to be 1. So this kind of representation can be seen as a distribution in a probabilistic sense even. And because we have kind of this relaxed distribution or representation, we also need a bit more general operations. So we use the blockwise circular convolution and correlation for the binding and unbinding respectively. And we use the simple sum and normalization for the bundling. And for the similarity, we use either the dot product or a novel L infinity based similarity. Interestingly, the binary SBCs is actually just a subcategory of our generalized SBC. So when initializing binary SBCs, we can use all those operations and yield the same result as with the binary SBC operators. So as a next step, we went to...
Michael, I'm sorry, just sorry for interrupting. Just to increase my understanding, why do you still call it sparse?
It depends how many vectors we like. Actually,
I mean, to me, it's a block structure. I mean, dense block structure of normalized block.
Yes,
vectors.
yes.
Concatenated blocks.
Yes, we don't have a guarantee for sparsity actually. We actually also played a bit with like having a bundling that again sparsifies the output, but it was for us not helpful. What is sparse in our case actually are the seed vectors. So actually our seed vectors are binary SBCs. And as a result, still when working with internally in the factorizer, those vectors are still somewhat sparse, but they can be sparse, but not necessarily, yes. But we can introduce a let's say bundling operation that embraces, or actually, yeah, it can embrace the sparsity if you want to.
Okay, thank you.
So we then went on by introducing a kind of block codes factorizer that is able to factorize those block codes. Let me just quickly go through the individual steps. So we have the unbinding, which is the circular correlation in this case. I just show an example with 2 factors for simplicity. Then we have the similarity search. This can be either the dot product or the L infinity search. We then do sparsify the resulting attention vector. And then comes the conditional random sampling, which was a bit more involved. So the thing is, because we have somewhat a fixed threshold and we pass our attention through this threshold, it actually can happen that all of the output values in this attention vector are zero. And what we do then is we simply initialize this output vector as a random vector where we set A randomly selected elements to 1 over A. It's kind of a uniform distribution where we simply select A then to be non-zero and others are zero. So it's just kind of a restart of our approach. And then we do the reconstruction, again, where we have as the output a normalization and no kind of sparsification or quantization, which was actually quite necessary to have the factorizer operating. As I said before in the question, the code books are still binary sparse block codes. So as a next step, we could analyze our factorizer performance on synthetic products. So in this case, we factorize two products with two factors. And we increasingly add complexity in the factorizer by adding our methodologies I already presented. So at the very beginning, we see the performance when using binary sparse block codes with the dot product as similarity and no thresholding and non-linearities. And we see that with increasing problem size, the accuracy drops quite rapidly. When replacing the binary SBC with the real valued, our GSBC, we actually can already achieve within 1 decade a bit of a better performance. This performance can actually be improved quite significantly when using this L-infinity based similarity, and even more when using the thresholding and sampling, which is the green line. This is also reflected when we look at the number of iterations on the y-axis down here, still with increasing problem sizes. Here we actually see that with our best performing configuration with the GSBC and this L-infinity, we can for at least a decade perform perfect factorizations with only 2 iterations. One interesting kind of angle of our new BCF is that we can operate it in a random search and superposition, where which gives us also quite a bit of insight into the functioning of the factorizer network. So what do we do here? Essentially, we break the iterative loop, and we always start with a random initialization. We then pass this random guess or initialization through the network. And if we converge in that iteration, we are done. So if we kind of detect that the current, let's say, bundle of estimates contains the true factor, we detect it as a convergence. And this allows us to actually compute the expected number of iterations it would take to do the factorization. And indeed, by configuring this our BCF as a random sampler for different dimensions, we are getting quite close to those theoretical estimations. It starts, this estimation starts to fail as kind of the bundling capacity is met. And so we see it especially if we increase the dimensionality, we have higher bundling capacity, and therefore we are also longer close to the theoretical expectation. So as we analyze the new BCF on synthetic data, we now can integrate it into the CNNs. So I will quickly explain you how the training and the evaluation looks like. So in the training, again, we have training data, which we can map with the convolutional layers to a query vector. On the other side, we have the target label, which we can map to 2 different factors with a random assignment, let's say. This assignment is arbitrary in this case. We can then generate the target products using the code books and train the convolutional layer using a novel block-wise cross entropy loss. During inference, we map an unseen image again to a query vector. We compute the blockwise softmax. So thanks to the use of these generalized sparse block codes, actually when passing an arbitrary vector through a blockwise softmax, you get a valid GSBC code, which is actually quite nice. So that's why we can simply feed this vector through the block code factorizer, and the resulting estimated factors can then be mapped again back to the predicted labels. So coming back to the example, or like the chart that I showed at the very beginning, where we have seen that bipolar factorizers cannot accurately factorize these kind of noisy queries from the neural networks. With the GSBC and brute force, we can also maintain a high accuracy, as we have seen it with the bipolar brute force. However, in this case, we also see a high accuracy when we apply the factorizer. So this factorizer used on average like 15 iterations to solve the task. And we could even constrain it to only use 3 iterations, and still we could see a high accuracy just within 0.1% by using only 3% and 3 iterations. So to conclude this part of the talk, we have detected the problem of bipolar dense factorizers, which seem to face challenges when their queries are somewhat noisy, and noisy queries could come, for example, from an approximate mapping from neural networks. Therefore, we introduced a new generalized sparse block codes, where we also have a new L-infinity-based similarity, which proved to be quite useful and helpful in the sense of factorizing sparse block codes. Then we introduced the novel block code factorizer, and which can factorize extremely sparse block codes. So the number of blocks in our cases were up to 4 blocks. So this is extremely sparse. We also could factorize noisy query vectors from neural networks, for example, and we saw that it requires very few decoding iterations, and in some cases only 2. And it also achieved our overall goal to maintain a high accuracy in the CNN integration on the ImageNet 1K. So we could save up to 44% of the parameters, and we could also save computation by requiring as little as 3 decoding iterations. And with that, I would like for now open the floor for questions, and then we can now afterwards continue with Giacomo's talk.
Yeah, so let's use next 5 to 10 minutes for Q&A to Michael. So any questions?
Oh, could I ask a question?
Sure, Chris.
Yeah. Thank you for the great first half of the talk, Mikhail. I was wondering about on the number of iterations point with the kind of random initialization, if you have plots about the variance of the number of iterations that would it take for a given problem size, like, or if you could tell me a bit about that.
So
then I'll tell you why. Yeah.
You mean in this case?
Yeah, or in the previous, I think, or I forget if it's previous or later, but you had some plots showing the number of iterations. Yeah, like
maybe
plots.
rather here. Yeah.
Yeah.
So at least if we like are in, like, first of all, I do not have plots with variances, but what we have seen is, at least with the two iterations down here, this is the bare minimum of iterations that you need, right? Because you first start with an estimation and you need to validate it to detect somewhat a conversions. So this is the absolute minimum that you need. And otherwise, yeah, it's quite spread, right? So it can like in some cases can already solve it with 2 iterations, but sometimes it can get close. So what we do actually here is we maximize the number of iterations, such that we do not more searches than what we would do in terms of brute force searches. So if you look at the factorizer network, in each step we do somewhat similar a number of similarity searches, right? And we constrain that the overall number of searches is strictly less than the number of searches that would be required with the combinatorial search by searching through all possible, because this is always on the table, right? So theoretically, one could always just search for all the possible combinations and we would have perfect capacity, right?
Right. Like, I'm curious because you describe it as conditional like restart. We can chat more about this offline, but I've done some similar experiments with resonator networks where, I mean, just also doing a form of conditional restart, but it's with the complex valued variant. And
Okay.
there, I mean, also significantly beats kind of the brute force. So, I mean, you need to start from a different initialization, but as in your case, it's pretty easy to kind of check. So, like, I'm just thinking like between the resonator network and the in-memory factorizer, I'm tempted to conclude actually the capacity, if we, want to characterize that in terms of a fixed dimension and in terms of like the number of like compute cycles you need to have. I mean, there might be some differences with the sparse activation part, but I think that they might be like pretty close or closer than might initially be expected, but can hash that out more. Yeah.
Okay, yeah, I think it depends on the thresholding, right? If you kind of have a somewhat an aggressive thresholding, this would yield you many restarts here, right? So I think it's a bit of a balance. And actually, what we did in our case was that we simply kind of somewhat brute force the search for like ideal threshold and the kind of A here by doing Bayesian optimization for like solving it as an optimization problem to find the optimal kind of hyperparameters for these two cases. That balances.
Yeah, that's really interesting that you did that experiment. So yeah, nice.
Okay, thanks.
Well, obviously I will ask for more questions, but I have one question of my own. With respect to the meaning of these vectors that you learn, I mean, in the superposition, I mean, that you factorize, I mean, how do you interpret them? I mean, so is one vector you learn typically learns the color, or what kind of features you, I mean, each vector or each codebook learns?
Yes. So for now, we really have this random assignment. So let's say in ImageNet, the class number 0 corresponds to factor 0 for both like factor 0. Then for 1, it has 0, 1, and so on. So this is really a random assignment now. But this actually would be quite some
for
future.
I understand that, but I mean, you started your presentation from factorizing different characteristic of an object like color, shape, etc., and then you transitioned into this realistic images. So my question is more how, I mean, so do you learn anything interesting semantically in these different vectors, or?
I would say so far not, because we really have this fixed assignment at the very beginning, which means like we really like we define this class to factors assignment at the beginning, which is somewhat arbitrary, and then we stick to it. But it would be actually very interesting to change this assignment as we are learning, right? So one might not only change these convolutional layers, but maybe in the mid of training, look at the, as you say, at the semantic space, or like how it looks like, and then maybe do some reshuffling of the class to factors assignment and also the target product vectors in order that we even could achieve better results.
Yeah, because I remember, I remember the time I collaborated with a group in Moscow, and we tried something like that. So we tried to learn, so basically to factorize different features of an object, so to say. But I mean, somehow, I mean, the results weren't very promising. I mean, on real images. So yeah, and that's why I'm asking. Is maybe you kind of saw something different.
We obviously thought about it, because it would be quite an advantage of this approach. But like, let's say the ImageNet might not be the best candidate to do that. We also looked into the Cube data set. This is this birds data set where you have like different features, and you have like the overall classes and also the corresponding features like kind of black tail or so on, or which kind of feathers and so on. This would be interesting, but that data set is also not that straightforward to be applied here, as we found. But yeah, would be actually very interesting.
Okay, let's see. We have a room for a couple of more questions before we continue with Giacomo's part. Anybody? So Ross switched on his camera. He
I'll
has
do it.
questions by default. Yes, of course. So yeah, shoot.
Yeah, looking back at the your GSBC
Yeah.
slide. So yeah, let's stop at that one. Yeah, thanks. So let me get this right. You're doing this blockwise. Yeah, okay. So that's blockwise circular convolution. So you're treating the set of indices within one block as basically constituting the input, one of the input vectors to your circular convolution. Is that right?
Yes. So
Yeah,
as
okay.
I said, like it's kind of the modulo L. Like if this vector would
Yeah.
be fully binary, like binary
Yeah.
stars, they are the same. They
Yeah,
are the same.
I'm still wonder why you call them spars.
But I mean, yeah, okay. So I mean, from the point of view of circular convolution and circular correlation, yeah, as long as the inputs are vectors, they're happy and they'll do what they do. But when sparse block codes were introduced, one of the interpretations, and this is really just a question about your thoughts on a topic. It's not a really hard question. You could treat each block as effectively being one element of a complex valued vector. And so the indices were essentially discretized phase of the one complex element. And which is why the modulo L sum works. So my question is that, okay, if we're taking a circular convolution of our degrees of belief in each of the possible phases of one element, that just seems a bit of a weird sort of a thing to do, but obviously it works. And your thoughts on what it's doing there, or why? Yeah.
That's actually a very interesting question, because in other work, like also when Giacomo will be presented, and we started with F frequency holographic reduced representation. And actually what we see there, especially when we do the bundling, a bit different things happen. So if you bundle, let's say, two collinear vector phasors, they cancel out, right?
Yeah.
Two opposite phasors.
Yeah.
But here in the GSBC, we don't have this effect, right? Well, the question is then, like, what are opposite vectors here in this case? But such like canceling out does not happen. This was actually very important for us when we then go to the reasoning.
Actually, that's interesting. I mean, the canceling out bit, because sorry, when you're bundling. So if you're bundling two items of opposite phase, then they cancel, and that's Penty's old XOR. What's the word? Tie breaking in when you're So basically, it was, well, if I've got with spatter code, binary spatter code, you've only got the two values. So effectively, you've discretized the phase down to two levels only. And so if you're bundling together the two opposite phases, then they cancel out. And so what are you going to do? You can't represent zero in the binary case. So effectively, you choose one at random. And I'm wondering if there's a relationship there between that and your, or could be some sort of similar use to your conditional random sampling, that effectively, if the if the phases cancel out on bundling at a blockwise level, essentially you're forced to choose a random value.
Yeah, that's a good point. I'm not fully sure about it, honestly.
Yeah, no, fine. It's
Let's say what mainly drove us towards this representation is really the bundling itself. Because here what we do here is we have some weights and we have a weighted bundling that we perform. And actually this it's a bit of a different topic, but we need to have very sparse block codes. We need to have very few blocks, which means, let's say, if you would bundle four of those binary SBCs, then it becomes quite tricky to represent all of the four vectors in this very sparse representation. And that's why we went then to a relaxation where we even also can weight the individual elements. This was our main purpose to do that.
I wonder. Well, probably let's. As a moderator, maybe I can decide so that we continue with the second talk, so that we don't lose our audience, and then we return to the discussion, because I personally find this topic very interesting. So we can talk, a lot about it. Just as a last message, so please, Michael, please look at the chat. So Chris put some
I can also respond
references. So that's could be some interesting discussion about it. So Giacomo, please.
Okay, so hello everyone, I'm Giacomo, and today I'm going to present our work on that was called Towards Learning Adaptive Reasoning using VSA distributed representations, that was presented in September at the NESI conference in Barcelona. So, contrary to Michael, I will now focus more on the reasoning part of the NBSA model. And in fact, this work was kind of an improvement of the reasoning backend of NBSA, basically. In particular, it was kind of a demonstration, a transition from knowledge representation embedded into the model to a first kind of a demonstration of learning, like in the context of NBSA, of how to learn learning to reason with VSA in this case. So wait, okay. So first, let me start with some introduction for those of you who might not be familiar with the task that we used, which is Raven Progressive Matrices, or for short RPM, which is basically this well-known human IQ test, where each sample is a 3x3 input matrix of 9 input panels. And the task basically is to find how and what belongs to the empty panel in the bottom row. So in each panel, there are possibly many objects which are basically represented, defined through a set of attributes, which are, for example, shape, size, and color. And the relations between these attributes across different panels are governed by a well-defined set of rules. So, for example, in this case, we would have that the color of the objects and their size remains constant within each row, whereas, for example, the number of objects in the third panel is given by the sum of the number of objects in the first and the second panels. So once we find the underlying rules, we can execute them in the final, in the third row, basically, and predict the missing panel of the input sample, which is selected within a set of 8 candidates, which are also given by the task itself. So one possible approach to solve RPM is through abductive reasoning, where abductive reasoning is basically a logical process that, given a set of evidences or observations, aims to find the simplest and yet most likely conclusion that can explain the evidence itself. So in the case of RPM, we consider the evidence to be the RPM sample itself, and we need to formulate some hypotheses on the rules that govern the relations between these attributes in different panels, in such a way that they best explain the sample itself. So coming back to NVSA, it was the NVSA represented from Michael, represented the first probabilistic adaptive engine that was using distributed representations, and it was, as he reminded before, composed of two different modules. So a front-end neural perception that allowed to basically extract these attribute values from the input panels, which are given as in a visual fashion. So they're images basically, and then project them, like translate them in this high-dimensional feature space, which is given by VSA vectors. And then with these, basically, these are fed into the backend reasoning, where the model can perform kind of rule detection and execution to finally predict the missing panel of the input of the input RPM sample. So other than achieving a kind of state-of-the-art performance in this dataset, NVSA also reduced the compute time required for the inference by 2 orders of magnitude with respect to basically the corresponding SOTA state-of-the-art neurosymbolic baseline. And but it had a limitation, which was basically that basically the rules that were used in the reasoning backend were hard-coded into the model itself. So this was not a limitation just of NVSA, also other existing VSA-based approaches, but not only, also like many other neurosymbolic systems encode the rules used for reasoning statically into the model itself. So they're considered kind of some prior knowledge which is given to the model and that the model can leverage to perform the computation and solve the task. In this work that I'm going to present today, what we did was basically improving on the NVSA and retaining some of the benefits that it had, such as, for example, the probabilistic abductive execution of the rules and the possibility to represent kind of like basically like all the rules which are used in RPM. So this kind of arithmetic rules and distributory, which is like a kind of a set rule and so on. And at the same time, it also improved the kind of rule representation because it allowed to learn these rules in a data-driven fashion rather than just encoding them directly into the model itself. So how did we actually do this? Well, before answering this question, I want to take a step back and understand how we can actually translate the task visual attributes into this high-dimensional feature space of VSA vectors. So in this work, we adopted the same trick that was used in MVSA, and basically for each attribute and panel, we encode each attribute of each panel basically in a single VSA vector, which is given by the superposition of all the possible values of that attribute, weighted by the probability of being in a specific panel. So to clarify this, basically, we can, for a specific panel in the input matrix, we can basically through, for example, a neural component and so on, extract a probability distribution basically over all the possible values of that attribute and obtain this PMF. And with this, basically, we can use it to compute this weighted banding of all the vectors in the codebook in our like fixed codebook for that specific attribute, and obtain the representation of these attributes basically in that specific input panel as this weighted superposition, which in this case, for example, would be taking 0.2, the VSA vector corresponding to the square, and plus 0.8 of the VSA vector corresponding to the pentagon. So once we do this translation into the VSA space, we can have a look at how the rules underlying RPM samples can be represented with our VSA algebra. And we observe that in practice, all these rules can be represented basically as sequences of binding and unbinding operations between vectors which represent the attributes. And these rules directly have like these kind of sequences of binding and unbinding operations when we initialize the vectors in our codebooks with a fractional power encoding scheme. Basically, we kind of create a bijection between the space of the VSA vectors and the real domain. So all these rules basically have direct real value equivalent, basically, which is, for example, correspond to the sum of the values of the input attributes or the subtraction and so on, basically. So at this stage, what we observed was that all these rules were kind of instances of a more general rule template, which was composed, also in this case, by a series of binding and unbinding operations between these vectors, where we needed so many terms to basically like be expressive enough to represent all the rules which were used in RPM. So at this point, basically the problem of learning the rules from data could be reformulated kind of as an assignment between the input terms, the terms in our general rule template and the panels in the input matrix. So basically what we wanted to achieve was basically assigning each input vector to one of these terms in such a way that we could kind of compile all the rules of RPM, like one rule for each one instance of this general rule for each rule of RPM. So this assignment problem, one way that we have to kind of express it is to have like a convex combination of the input panels for each one of these terms, where basically over the different panels in the input sample, where in this case we distinguish between some kind of input panels for which we want to predict the third panel. So like two panels for which we want to predict the third element, which are here marked in blue. And then some context panels, which are used as some kind of working memory to compute the correct solution, because some rules also requires to have comparisons across different rules, such as distribute tree, which are here shown in pink. And then finally, also we have in this convex combination also the binding identity vector, which is kind of used as a filler to fill the unused term in the general rule template. And then in particular, in this weighted combination, basically, the yellow terms are the weights that we effectively need to learn during the training of the model. So another way to show this is basically if we consider this to be the matrix of the input, like for a specific attribute, basically, the RPM matrix becomes like just a matrix of in vectors, VSA vectors representing the attribute value for that specific panel, and then the binding directory. So what we want to achieve is to have basically like an assignment of like some of these terms into the general rule template. And then of course, which is given by this weighted basically convex combination of the vectors for each one of these terms, where we learn the weights in this convex combination. And then of course we need to do this in parallel for R different rules, where R is basically varies across the different dataset, might be different for other datasets. And in the case of RPM, is 5 because we need to learn 5 different rules concurrently. So one direct advantage of this problem formulation is basically that it allows to interpret the rules that are learned by the model, and we showcase kind of this behavior with a simple example that was directly extracted from one of the models that we trained. And when expecting the distributions of the learned weights, basically for each one of these terms, we can see that these are extremely sparse, and that all the terms in this template tend to converge quite early during the training to a specific input panel during the training, basically. So we have that each term in this general template is assigned to a single corresponding vector in the between those who are available basically in the learning. And then coming back to this learned rule, it might not seem so interpretable at first glance, despite what I just told you. But one thing that we can do is, of course, like to simplify the common terms in the two branches of this general template, since they kind of cancel out because of this unbinding operation. And if we simplify this, basically, we can quickly observe that this is nothing else than just the progression rule of RPM. So again, like this is very nice feature of the model, which is basically that we can, once the model is trained, we can actually inspect the rules that it learned and understand the dynamics and what it actually learned, and if what the model learned is actually corresponding to the true rules of RPM. So now, like to have a kind of a deeper look at how the inference works in the model in practice, the first step is kind of context, what we call a context augmentation procedure, whose role is basically to abstract away the absolute positions in the input matrix. So if you remember, when I first introduced like this kind of like learning the rules as an assignment problem, I had like different categories of vectors. Like I divided between the current sample, the context panels, which are used as working memory and so on. And this is basically why I did that division, because in practice, we want to make this division basically because we want basically like for each one of the rows, basically, we assign different input panels to each one of these categories. So for example, for the first row, we consider as like the current sample, the first 2 panels of the row, and then all the other panels available, so the other 5 panels, as the kind of context panels in support of like to support the prediction for that row. And then we do the same basically for the second row and the third row, where we take the first 2 panels of the second row and the others as context, and so on, basically in the same fashion. So the core benefit of why we needed to do this abstraction kind of is that it allows us to share the same set of rules across all the rows of RPM. So what we can do is basically to learn a single set of rules and then like perform inference with them in any of the rows of an RPM sample. But why do we need to share the rules across the row, and why do we need to perform inference on all of them if we are just interested on the third one? The answer is that basically for every attribute, the same rule is applied to every row. So one thing that we can do is a selection we can implement basically in our model is a selection mechanism that chooses which rule to apply in the third row based on how the same rule basically worked on the first 2, which are basically examples of how that rule is applied. So in practice, this corresponds to having 2 parallel steps in the forward execution of the model. So we have an execution step where we kind of execute all the rules together. So we have like a dictionary of rules, like this are different rules that we learn during training. We apply all of them in parallel to the third row of the RPM sample and get three different, are different results, which are the results of the application of all these rules. And then the second step is a selection step, which basically the same set of rules is applied to the first and the second row. And then in this case, we actually have the ground truth of the application of the like for these two rows basically. And what we can do is like compare them with the results of each one of these of these rules, and then compute some confidence values, we could call them, for each one of these rules. So basically, using the first two rows to compute confidence values on which row is actually which rule is actually applied for this RPM sample. And then these confidence values are basically used to compute a weighted superposition of the results of this execution. And finally, we compare these results with available candidates and pick a final prediction for like the missing panel of the RPM sample. So turning to the empirical evaluation of the model, we tested it against a wide range of both symbolic and neural baselines. And our model achieved the best in-domain accuracy on the RPM dataset across all of them, despite having orders of magnitude less parameters compared to the other models, which are kind of learned, where the rules are not like encoded into the model itself. And then the same was also the case when we tested it on a kind of unseen rule attribute pairs, so in a out of distribution setting, we could say, because in this case we compared it against an MLP baseline, which whose performance dropped quite badly, basically, in this kind of scenario, which was a sign that the model was not really learning some effective rules, but it was taking like some kind of shortcut during training, or basically like they learned that it wasn't really kind of learning to reason, we could say, with the true set of rules. And then we also tested it with GPT, in this case GPT-3, and it performed surprisingly better. But we suspect that this might be due to some data contamination, because then like further enhancing the prompts, so using more complex prompting strategies, and so trying to improve basically the performance through this kind of means, didn't achieve any results. So it only worsened the performance, and so yeah, we suspect this is mostly like a sign that there might be some data contamination, because RPM is by now well available online. And then finally, our model achieved close to perfect OD accuracy on this unseen rule attribute pair combination on every unseen combination, basically. So we also tested this model basically on another type of auto distribution. So in a kind of a variation of the standard iRaven dataset. So we have this kind of newly introduced dataset, which is called iRaven X, where we basically extend both the length of the input sample. So we have like always three rows for an RPM sample, but we have much more terms in these rows. And also we extend the kind of the dynamic range of the single attribute values that the attribute values can assume in each one of the panels. So we kind of also like extend it to unseen digits. And what we see in this case is that state-of-the-art language models, such as in this case GPT-4 and Llama 3 70 billion, their performance rapidly drop with like this kind of unseen in this kind of auto distribution settings to even below 10% regimes, whereas our proposed model, when we actually program it with like the true rules, because we can also do that, like program directly the weights in such a way that basically like we program the rules that we want to represent in these like weighted combinations. And in this case, the model retains perfect accuracy, which is mostly due to the FP initialization of these basically the representation of the attributes through this FP initialization. And then also our learn model, it has some degrade, but degrades much better, more gracefully than the LLMs. And this was part actually of another work, which is actually right now under review for the Neurosymbolic Artificial Intelligence journal. So this was a separate publication actually with Michael. And yeah, so that was more or less it to wrap up my talk so far. Today I presented this novel approach that can basically learn the rules underlying RPM tests from data as this kind of assignment problem in the VSA space. So this approach outperformed a wide range of connectionist and neurosymbolic baselines, and can learn perfectly explainable rules, because we can actually investigate what the model is learning and how the what are actually the rules that the model is learning down in explainable fashion. And then this model also use orders of magnitude less parameters compared to all the other approaches that we benchmarked against. So I didn't have time to cover it in this presentation, but we also studied, basically, we also were able to show transfer learning across different constellations, which are basically different arrangements of the objects in the input matrix, which resulted in basically needing just one, reducing basically by 85% the amount of training data required, because we could just train on a single constellation and generalize the results for all of them. And then, as I said before, the model could also be programmed with prior knowledge. And we also had some experiments where we could basically learn incrementally on top of it. So program it and then still perform like some kind of learning, and like the performance will not degrade. And then finally, we also show some robustness to different weight initialization. So like initializing the initial convex combination with different weights still led to convergence basically for all the different initializations. So that was it. Thanks for your attention. And yeah, these are the pointers if you're interested in the work. And we also have open source code that you can check and play with. And yes, that concludes my presentation. And yeah, if you have any question, feel free to ask. Thanks.
Absolutely. Thank you, Giacomo. Thank you. Questions, please? Mincio, please.
Hi. So I personally don't really work with VSA, so my understanding was a bit limited. But
Yeah.
do I understand it correctly that the number of rules that the network is going to learn has to be set by the modeler?
Yeah, exactly. Like we still, the number of rules is still an hyperparameter that can be set basically depending on the dataset. In the case of RPM, it's like 5 rules. We set it ourselves. In other dataset, it might vary. Yes.
Yeah. And the types, sort of like qualitatively different types of rules, are also in some sense somewhat limited, right? So you can have, I don't know what types of rules you had there, but yeah, those 5 different things, is that basically it? Or like, is it also possible to somehow come
Yeah.
up with like something?
Yeah, this is a good question. Thanks.
Yeah.
Because yeah, like these are basically all the rules of RPM. So we just needed basically to represent this kind of relations to actually solve RPM, because these are the kind of relations which are used in this task. However, it is true that right now, like with this kind of series of binding and unbinding operation, we are kind of limited to just additive relations between attributes. So we can mostly represent just additive and subtractive relations, or as in the case of distribute tree, some kind of set operation. So understand like which element of a set is missing, basically, as is the case for distribute tree. But we're actually currently working on expanding basically the representational power of these rules. Yeah.
I see. Yeah. All right. Thank you for the talk.
Thanks.
So let's check if we have more questions to Giacomo or Michael. Well, let's see. So nobody. Maybe one question from myself. Did you have plans to apply to other data sets, or somehow it's complete? I mean, it's similar question to the previous one. I mean,
Yes. I mean, the current main limitation is exactly like this kind of expressiveness, and but yeah, we are like currently investigating like possible ways to develop it and then apply it to other datasets where basically also like the relations between attributes and in general like the representational power which is required then is greater than the specific case of RPM in this. Yeah.
Okay. All right. Okay. If there are no more questions, so this is the last chance to ask. In this case, let's end this talk. I would like to thank you very much, both Giacomo and Michael. Thank you guys for giving this, sharing this great material with us. And I think eventual questions should be directed to you offline. If possible, Giacomo, if you can share the URLs to, I mean, behind this QR codes to me that I can update the website. So I mean, I decided not to link the PowerPoints, but the links to GitHub and the actual article would be appreciated very much.
Sure, will do.
Yes. Okay. So maybe the very last message from my side. So I'm working on the program for the upcoming season of VSAONLINE. So if you have any ideas of individuals you want to hear about some interesting work or anything, so please drop me a line. Otherwise, I will construct a program in my smaller circles with Rose, Dennis, and others. But for now, thank you very much, and see you in 2 weeks from now. So a pre-announcement, we will have a new group presenting, so a group from Norway. So please come and listen. So see you in 2 weeks from now. Thank you, and goodbye.
Thanks. Goodbye.
Bye. Thanks.